In a hydraulic lift, if the radius of the smaller piston is 2 centimeters and the radius of the larger piston is 20 centimeters, in order for the lift to remain in equilibrium, what is the maximum weight that the larger piston can support when a force of 250 newtons is applied to the smaller piston? Let's start off by listing the information we have at each point. We are interested in how much force the large piston can support. Let's have a reference point at the bottom of the large piston that we will call point 3. So we now have points 1, 2, and 3. Point 1 is located at the bottom of the small piston. Point 2 is the point directly below the large piston, but at the same level as point 1. Point 3 is the point we added to the bottom of the large piston. Since the small piston is supporting 250 newtons, we know the force the bottom of the piston exerts on the liquid at point 1 is 250 newtons. We'll call the radius of the small piston R1. R1 is 2.0 centimeters. The area of the small piston is called A1. A1 is pi R1 squared. The pressure at point 1 is due to the atmospheric pressure at that point and the force per area on the small piston, F1 over A1. Now the large piston has to support a force that we can measure at point 3. We do not know this force yet, but it is the force we are trying to find. So we'll say F3 is unknown at point R3, where we'll call the radius of the large piston R3 equals 20 centimeters. Notice that this is 10 times the radius of the smaller piston. The area of the large piston is A3. A3 is pi R3 squared, which is pi times the quantity 10 R1 squared, or 100 pi R1 squared. The pressure at point 3 is due to atmospheric pressure at that point and the force per area on the large piston at point 3, F3 over A3. Recall that the pressure at a point in a static fluid of constant density is equal to the pressure at reference depth plus the product of the fluid's density, the free fall acceleration of gravity, and the difference in depth between the 2 points, where h is positive if the reference point is above the point of interest, and negative if the reference point is below our point of interest. In this case, since point 2 is below our reference point 3 and at the same level as point 1, h is taken to be positive. Rewriting this and substituting our expressions for P1 and P3, we have P1 being the sum of atmospheric pressure and F1 over A1 equal to the sum of P3 and the pressure difference given by the product of density, gravity, and height, where P3 is just the sum of atmospheric pressure and F3 over A3. Since atmospheric pressure appears on both sides of the equation, they cancel out. We now have the ratio of F1 to A1 equal to the ratio of F3 over A3 plus rho g h. To isolate F3, we move rho, g, and h to the other side of the equation. Multiplying through by the area A3 of the larger piston, we have the ratio of the areas of the larger and smaller piston, A3 over A1, times the force supported by the smaller piston, F1, minus the product rho, g, h, and a. This is the expression for the weight that the larger piston can support if there is a height difference between the two pistons. The greater the height difference, the less weight can be supported. The difference in height means that the smaller piston will need to support a larger amount of force due to the pressure differences between the bottoms of the two pistons. Since we want the maximum weight that the large piston can support, and since we only have 250 newtons to work with on the smaller piston, we will set h equals 0 such that there is no height difference between the two pistons at points 1 and 3. This leaves us with the force on the larger piston equal to the ratio of the areas of the two pistons times the force supported by the smaller piston. What this statement reveals to us is that the ability of the larger piston of a hydraulic lift to support a weight is directly proportional to the weight supported by the smaller piston, where the constant of proportionality is the ratio of the areas. For example, if the area of the larger piston is 5 times as large as the area of the smaller piston, then the larger piston can support 5 times the weight. In this case, the area of the larger piston is 100 times the area of the smaller piston. So this is going to reveal to us that the larger piston can support 100 times the weight of the smaller piston. You can see this after plugging in our expressions, dividing through by pi, canceling out r1s, and simplifying. After simplifying, you can now see that the force supported by the larger piston is equal to 100 times the force supported by the smaller piston. After plugging in numbers, we have that the larger piston can support a weight of 25,000 newtons.